All right, so we're going to balance the two reactions we've seen so far. The zinc and copper, our first example, and the cobalt iron one. And we're going to do this with the half reaction method, which you guys hopefully learned last semester in that RedOx chapter that we discussed. Hopefully it's just kind of retraining you a little bit. Again, the best part is we don't have a bunch of oxygens and OH groups and hydrogen ions to get rid of on these. It's just straight up metal ions. So that simplifies everything quite a bit. But we are going to keep the same process in mind. We have to find out how many electrons are produced by oxidation, how many are absorbed by reduction, and make them match. Okay, so we can't just hunt and peck and find coefficients that work for redox reactions because they have to be both mass balanced. Mass balanced is the kind of balancing that we've done already. Just balancing a chemical reaction, that's mass balancing. Same number of each atom on each side of the arrow. But they also have to be charge balanced, which means the sum of the oxidation states on the left has to match the sum of the oxidation states on the right. And it's not just any random group of coefficients that'll make that work out. So we're going to look at that copper and zinc process that was in that first galvanic cell picture that I showed you. So in that process, zinc was oxidized. So we started out with zinc, and it became Zn2+. It was oxidized. At the same time, copper was reduced. So copper aqueous absorbed 2 electrons to become Cu as a solid. Remember, all of the elements have 0 oxidation state. So zinc went from 0 to 2+, copper went from 2+ to 0. So both of these are 2 electron processes. So this is the simplest kind we've got for balancing them because you have the same number of electrons reduced as oxidized. But we're going to use this one to illustrate our half reaction process. If you follow the same setup every single time, things will work out great. Okay? So we split this into half reactions. And they call this kind of equation balancing the half reaction method. You probably heard me use it last semester when we did those more complicated redox processes. We split them into the reduction and the oxidation portion. It does not matter which one you write down first. On this one, I chose reduction first. So we look at our equation that's up here. Sometimes we have a picture, which is great because it tells us what's reduced and what's oxidized. But most of the time, you're given an equation that you have to balance. So we have to find out what's reduced. So just looking at this from scratch, we need to find the element or the participant that went from more positive on the left to a more negative oxidation number. And that's copper in this case. Copper went from 2+ to 0. So Cu2+ plus 2 electrons, right? Because copper 2+ doesn't make copper as a solid until it picks up 2 electrons. So the reduction half reactions have electrons as a reactant. So plus 2 electrons produces solid copper. Each one needs to be mass balanced. Like I said before, 1 copper and 1 copper. Remember, electrons have a negligible mass. They have to be charge balanced, which means the sum of the charges on the left has to match the sum of the charges on the right. 2+ minus 2 is 0. Okay? If we had gotten the number of electrons incorrect, if we just wrote 1 electron or 3 electrons, we would still have it mass balanced, but it would not charge balanced because this is fixed at 2+. If we had 1 electron, we still have a 1+ left over, and that doesn't charge balance, so it can't be right. So now we have an individually balanced half reaction for reduction. Do the same thing for oxidation. Oxidation is the zinc half reaction. So Zn as a solid. Now the oxidation half reactions produce electrons so that they can be supplied to the cathode side. So Zn as a solid makes Zn2+ plus 2 electrons. Again, they have to be mass and charge balanced. 1 zinc and 1 zinc. The charge balancing comes about, the 2 electrons help us balance that because 2 electrons have 2 negatives. 2+ They cancel out, give us zero charge. Some is zero on the right, some is zero charge on the left. Okay, mass and charge balanced. So I said earlier, this is one of the easier ones because the electrons already match. The number of electrons in each reaction match. So when we add these up to balance it, we cancel what will cancel. In this case, it's the 2 electrons in each of the individual half-cell reactions. 2 are produced, 2 are consumed. So when we write this out, we write what's left over. Cu2 plus Zn as a solid makes Zn2 plus aqueous plus Cu as a solid. It does not matter what order you write the zinc and the copper in on each side as long as the charges are correct. Cu2 plus can come first or second. Zn as a solid can come first or second. On the product side, we can write the zinc first, zinc 2 plus, aqueous, or the copper first. As long as they're on the correct side of the arrow and the oxidation states are right, that does not matter. So this is the balanced electrochemical reaction for copper and zinc reacting this way. All right, I'm going to pause there. We'll come back with another one. We'll look at our iron reaction.